In this video, we will see the comparison between Otto cycle, diesel cycle and dual cycle when they are subjected to the same maximum pressure and same heat input. When they are subjected to same maximum pressure and same heat input, so which cycle will have maximum efficiency and which cycle will have least efficiency, and when do you get maximum work? We will see these kind of comparisons. So for these comparisons, I am drawing these cycles, the three cycles in PV and TS coordinates. So you can draw any cycle first. So first I am drawing Otto cycle. Otto cycle looks something like this. So 1 to 2 is reversible adiabatic compression process. So 2 to 3 is constant volume heat addition process. So 3 to 4 is reversible adiabatic expansion process, and 4 to 1 is constant volume heat rejection process. Constant volume heat rejection process. So we have two constant volume process and two reversible adiabatic process. I am plotting the same curve in temperature entropy diagram in TS coordinates. So 1 to 2 is reversible adiabatic compression process. It is isentropic compression process. It is an isentropic process, entropy remains constant, and it's a compression process, temperature increases. So 1 to 2 is isentropic process, entropy remains constant, and its compression temperature increases. 2 to 3 is constant volume heat addition process. So it's a heat addition process. So both temperature and entropy will increase during heat addition. This is 2 to 3. And 3 to 4 is reversible adiabatic expansion process or isentropic expansion process. Isentropic process, entropy remains constant. It's an expansion process, temperature decreases. And 4 to 1 is constant volume heat rejection process. It's a heat rejection process, both temperature and entropy decreases. Temperature decreases and entropy decreases during heat rejection. So this is Otto cycle in both PV and TS coordinates. So the constraints are like this: for same maximum pressure and for same heat input. Same maximum pressure, we can do the comparison for pressure in PV coordinates, and for same heat input, we can do the comparison for heat input in TS coordinates. So here he is saying that, so for same maximum pressure, it means, so the pressure should not be more than this line. Now I am drawing diesel cycle. So the inlet conditions are same. So inlet conditions depend on ambient conditions. Therefore this 1 and 1 dash, so the inlet conditions for Otto cycle and the inlet conditions for diesel cycle will remain the same. Now I am going for compression process. So here in diesel cycle, so the pressure increases only during compression process. So what I am doing is, so I am compressing this gas so till I reach the maximum pressure. I am compressing this gas till I reach the maximum pressure. So I reach maximum pressure here, 2 dash. So you can see here, so compression ratio for diesel cycle will be more than compression ratio for Otto cycle. So 2 dash comes here, it's more compression in diesel cycle. So inlet conditions are same, so therefore 1 dash will be here, 1 and 1 dash will be here. And compression in diesel cycle, for the same maximum pressure, you will be having more compression. Since we are having more compression, so this 2 dash will come here. And the second constant is for the same heat input. So this is constant volume process, and here I have constant pressure heat addition process. So constant pressure line have lesser slope in comparison with constant volume line. So slope of this line is less in comparison with slope of this line. These two are looking parallel, but they are not parallel. So this is constant pressure heat addition process. And the constant is that, so for same heat input, it means that whatever the area you are getting under the curve 2, 3, you should have same area under the curve 2, 3 dash. Therefore I am stopping this curve here, so 3 dash. So this area is exactly same as this area. So 3 dash will lie here. So this is constant pressure heat addition. After heat addition, I go for, so isentropic expansion process. I go for expansion process till I reach the initial volume. Once I reach the initial volume, I go for constant volume heat rejection process. So I reject heat till I reach the initial state. So this is 4 dash. So here you can see, so this 3 dash 4 dash line should intersect 2 3. So this is compression process. So I go for constant pressure heat addition process. So I go for constant pressure heat addition process. So this is 3. This point is 3. 1, 2, 3, 4. And this is constant pressure heat addition process. I go for constant pressure heat addition. This I am calling it as 3 dash. And then I go for expansion process. So this 3 dash and this is 4 dash. I go for expansion process till I reach the initial volume. Once I reach the initial volume, at constant volume I go for heat rejection till I reach the initial condition. 3 dash 4 dash curve should intersect this 2 3 line. It's intersecting this 2 3 line. So 3 dash will come somewhere over here. So this is how we complete the cycle. So in the same coordinates, so we'll try to draw this dual cycle. So inlet conditions are same. So 1 double dash will lie here. So I go for compression process. So here in dual cycle, we go for constant volume heat addition. So during constant volume heat addition, so there is some pressure rise. So if I compress, so from here to here, in dual cycle if I compress here, then I will not have any space for constant volume heat addition. Why? Because if I go for constant volume heat addition from here, so pressure further increases. So I will not go for compression till here, I will stop somewhere over here. So 1 double dash is here, so 2 double dash, I will compress till 2 double dash. So and then I go for constant volume heat addition. I go for constant volume heat addition, constant volume heat addition is done. I go for constant volume heat addition till I reach maximum pressure. So beyond that I cannot increase. So you can see 2 double dash is lying between, so 2 and 2 dash. So inlet conditions are same, 1 double dash will lie here. So I go for compression process such that, so 2 double dash is here. Once compression is done, I go for constant volume heat addition process. So constant volume line is more vertical in comparison with constant pressure line. Since this is more vertical, it will intersect this. So I go for constant volume heat addition, so till I reach maximum pressure. So this is 3 double dash. So once I reach maximum pressure, so then I go for constant pressure heat addition process. I go for constant pressure heat addition process. So whatever the area I am losing here, area under the curve 2, 3 dash must be exactly same as area under this red color curve. So red color curve is 2 double dash, 3 double dash and 4 double dash. So whatever the area I am losing here, so that area I am compensating here. This area is exactly same as this area. So this I am calling it as 4 double dash and this I am calling as 5 double dash. I expand so till I reach initial volume. Once I reach the initial volume, I go for constant volume heat rejection process. So now you can see here, so I added heat till I reach maximum pressure. So I reached maximum pressure at this point. So I am calling this point as 3 double dash. So at this pressure I go for heat addition process. And heat addition process in constant pressure, it's 4 double dash. 4 double dash lies between 3 dash and 3. So 4 double dash lies between, so 3 dash and 3 lies here. So this is 4 double dash. This is the state. And then I go for reversible adiabatic expansion process till I reach initial volume. So till I reach initial volume, I go for expansion process. Once expansion is done, this I am calling as 5 double dash. So at constant volume, I go for heat rejection till I reach the initial state. So this is how we complete the cycle. Now we have drawn all the 3 cycles. In all the 3 cycles, heat input is the same. So I can say like this. So heat supplied for Otto cycle is the same as heat supplied for dual cycle is the same as heat supplied for diesel cycle. Heat supplied is same in all the cycles. This is the constant we are seeing. But if you look at the heat rejected, so if you look at this curve 1, 2, 3, 4. 1, 2, 3, 4 is Otto cycle. 1 dash, 2 dash, 3 dash, 4 dash is diesel cycle. 1 double dash, 2 double dash, 3 double dash, 4 double dash, 5 double dash and 1 double dash. This is dual cycle. You can see here area under this 1, 4, that is heat rejection process. Area under 4, 1 is more in comparison with area under 5 double dash, 1 double dash is more in comparison with area under 4 dash, 4 dash, 1 dash. I can say like this. So heat rejected in Otto cycle. Heat rejected in Otto cycle, that is 4, 1. So is more than heat rejected in dual cycle, that is 5 dash 1 double 5 double dash 1 double dash is more than heat rejected in diesel cycle. I can say like this, area under the curve 4 dash 1 dash is the least. I can say like this, area under the curve 4 dash 1 dash is the least amount of heat rejected. So this is the least amount of heat rejected. So heat supplied is same in all the cycles. So in whichever cycle less amount of heat rejection happens, so that cycle will give maximum work done. I can say like this, work done in diesel cycle. Work done in diesel cycle is more than work done in dual cycle. This is more than work done in Otto cycle. So for the same heat input, work done is more in diesel cycle. Therefore, I can say like this, efficiency of diesel cycle is more than efficiency of dual cycle is more than efficiency of Otto cycle. When all the cycles are subjected to the constraints that, so maximum pressure is the same and heat input is same. So diesel cycle will give maximum efficiency and Otto cycle will give least efficiency. Thank you.